Today we are going to be looking at sample space, and sample space is just all the possible outcomes of an experiment make up a sample space. We're also going to be looking at some compound events which have two or more simple events combined, and that's the situation we have in the first few problems. And then also we're going to be looking at this idea of the fundamental counting principle. So we'll be using that concept as well. So let's take a look at these compound events. Compound events mean there's two things going on, and that's what's happening here. See, Joanna spins the spinners at right. So there's more than one event. One event would just be spinning this one spinner, but now we're spinning both of these spinners at right at the same time. And what is the possible outcomes that we have? So from these problems, we're going to end up understanding something about this fundamental counting principle that we're talking about here. And so what we might want to end up doing to start with is using a tree diagram. So I'm going to start with this spinner here. And so we could have an outcome of A with the first one. And then from the first one, we can look at, if we get an A, let me go ahead and fix this real quick. If we have an A, we could end up with answers from the other spinner of either 1, 2, or 3. Well, that's just if I select or spin an A, I could either have a 1, 2, or 3 pop up for the other spinner. Well, what happens if I spin a B with this first spinner? Well, I could have the same possibilities with the second spinner. I could either have a 1, a 2, or a 3. And then if I spin a C with this first spinner, I could still have the possible outcomes of a 1, 2, or 3 from that second spinner. And then I still have the D to go. And so again, I have those same outcomes of either a 1, a 2, or a 3. And so those are all the different outcomes, and they want us to list those. So a way to list them would just be to write down A, comma 1, and then we could write down B or A, comma 2, and we have A, comma 3. That would be one set. And then I also have the B, comma 1. I have the B, comma 2, and the B, comma 3. So those are the first 6 different possibilities. And then the next one would be C, comma 1, C, comma 2, and I have C, comma 3. And the last one would just be D1, D2, and spinning a D and a 3. And now they ask us, what is the theoretical probability of each outcome? Well, each outcome is unique. There's no outcome that is the same. See, they all have, if I spin a 1, I either spin a 1 with an A, a D, or a B, and this one's my B there, or a C. Same thing with the 2, either an A, B, C, or D. Same thing with the 3. So each outcome is unique. So the outcome of any of them is going to be 1 out of the total number. Well, how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total outcomes. Well, taking a look at these numbers here, you notice that we have 4 different values, 4 possibilities here. I want you to notice that. There's 4 outcomes with the first spinner. The second spinner, we notice these outcomes here. There are only 3 outcomes with the second spinner. Look at those numbers there, 4 and 3, and we'll come back to those. And how do they relate to the total number of outcomes? Let's see if there's an idea that keeps on popping up, because when you multiply these two numbers, we do end up with 12. So we'll come back to that in a little bit. Let's take a look at the next problem here. For breakfast, Armando has choices of pancakes, eggs, or cereal. So let's go ahead and write down P stands for pancakes, E stands for eggs, C stands for cereal. Now he has a choice of milk, so we'll use M. Hot cocoa, well, we've already used C, so let's use H for hot cocoa. Or juice. Those are his different choices. So let's go ahead and set up another tree diagram. We've got pancakes, or actually instead of a tree diagram, let's do this. Let's write down a chart going this way. So we've got pancakes, we've got eggs, and we've got cereal. Over here we've got milk, we've got hot cocoa, H, and we've got juice. So our different choices, we could use this to write down like PM, which stands for pancakes and milk. And that would be one of our outcomes here, pancakes and milk. And then we'd also have eggs, milk, so EM. And then CM. And then over here we'd have PH, EH. And then CH. And then over here we'd have PJ for the pancakes juice. EJ stands for eggs juice, or CJ stands for the cereal juice. Well, let's take a look at going ahead and writing those in there. We've got the same ones we had before, so just another way to set up that same type of chart. So we also have CM, and I'll write down the PH, and I've got the EH, and the CH, and then we also had the PJ, we had the EJ, and we had the CJ. Well, let's see what else they ask us for in this problem here. They also ask how many outcomes are in the sample space. Well, we can count them up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. There's nine possible outcomes. Well, let's take a look at this idea here. Notice that there's 3 outcomes here. So there's 3 here, 3 outcomes. And on the other side, there are 3 outcomes over here. So there's 3 outcomes here. Notice what the total outcomes are, 9. Notice that 3 times 3 equals 9. So there's a little rule there. Well, we'll want to use that on a problem like this. Take a look at this one. Here, Shannon and Tyler are playing a game that involves spinning the spinner, shown right, and tossing a number cube. See, those are 2 different events. That's called a compound event here. 2 different events happening at the same time. What is the probability that the number cube will land on 6 and the spinner will land on or stop on 4? We can use the same sort of idea here, and hopefully after this you'll kind of understand this fundamental counting theory. See, fundamental counting theory means instead of just counting, we've got a theory of counting, so we don't have to count each time. So let's go ahead and put the different values for the spinner over here. So I've got a 1, 2, a 3, a 4, and then it goes back again. 1, 2, a 3, and a 4. So there's 8 different choices here. And then over here we'll write down the number cube, or the die. So we have 1, 2, 3, 4, 5, or 6. Well, looking at this, if you remember a multiplication table, if you have one option here followed by 6, that'd be 6 different options. Here we have 2 followed by 6, that's another 6, that's 12. 3 is another 6, that's 18. That makes a total of, if I go ahead and count them all up, that would be 8 times by 6. That'd be 48 different outcomes. 48 outcomes. And so the fundamental counting theory works when you count up the number of outcomes you have. You have 8 here, and we have 6 here. We multiply those together, that would give us 48 different outcomes. Well, I'm just going to write down the 2 that pertain to our situation. So we have rolling a 6, so here's 6, and spinning a 4, so there's 4 and 6. And over here we could also get a 4 and a 6. So there's only 2 possibilities. So our probability of spinning a 4, spin 4, and roll 6, that would be 2 out of the total number of 48. And I got that because instead of writing them all and counting them all up, I see that there's 8 down this way, 6 this way. 8 times 6 makes 48, so 48 total. And I could just reduce the fraction to 1 over 24, and that would be my answer. So there's 1 out of 24 chances of this occurring. So the fundamental counting theory says you can multiply the choices together that you have, and that will give you the total outcomes. And we'll write that down in the next part.